So for standing waves in sound, you have to just keep in mind that we have two kinds of mediums in which we can create standing waves. What is called the open organ pipe, where both the ends are open, in which case both the ends are what we call pressure nodes. So if the length of the pipe is L and inside the pipe we have gas of temperature T and gamma, adiabatic constant and molecular mass M, then for the fundamental we know we have the formula 1 by 2L square gamma RT by M, because for the fundamental mode what happens is that the two ends are consecutive nodes and we have one pressure antinode in between. So the variation in pressure looks like this. So using this and this we get this formula for fundamental. Like that, the first overtone becomes the second harmonic. The second overtone becomes the third harmonic. And correspondingly, nth overtone is the n plus 1th harmonic. So the second overtone has the midpoint as a node and two antinodes in between. So all these general things that you already know. So in the second overtone case, this C is continuous. So this becomes the general formula. Whereas we also have another type of situation which is called the closed organ pipe. Which is basically an organ pipe with one end open and the other end closed. The closed end acts like a pressure antinode. This acts like a pressure node. So the fundamental situation, it is like consecutive antinode and node. L becomes lambda by 4, so this becomes 1 by 4L. Where L is the length of the tongue. First overtone is a situation where something like this. L becomes 3 lambda by 4 or lambda by 2 plus lambda by 4. So correspondingly the frequency becomes 3 by 4L square root of gamma RT by. So you can see that the frequency of the first overtone is the third harmonic of the fundamental. Like that, the second overtone becomes the fifth harmonic, and the nth overtone becomes the 2n plus 1th harmonic of the fundamental. So this becomes a general formula for frequency. So it's a standard thing like we've seen in the case of standing waves for strings also. If one end of the medium is node and the other end of the medium is antinode, then that means they are opposite type of boundaries. One is a rigid boundary and one is a flexible boundary. Then we always have standing waves with only odd harmonics. Whereas if both are nodes, then we have both even and odd harmonics. So that's the general formula. So let's see an example question based on this. Now we have some very standard kind of situation here. We have a glass pipe such that the top end is open, bottom end is closed, and say the length of the pipe is L. Okay, now what we are doing is to make it resonate with the tuning fork. We are also filling water up to a certain height, H over here. So this is the water level, and we are using a tuning fork a certain frequency to create the resonance. So what we observe is that the first resonance occurs for the height of the water column being 5 centimeters. The second resonance for the height being, which is 23 centimeters, and a total of 9 resonances are observed. Also, speed of sound in the air. Inside this is 340 meters per second. So from this, first of all, find the frequency of the tuning fork. and secondly, the length of the pipe L. So for that, assume zero end correction. So just try this out, people. Try this question out. Yeah, anybody got the answer yet? Work this out, people. Okay, so how to do this question? Let me start with a hint for you. Okay. So what you have to understand is that whenever there is a resonance happening, the concept of the question is like this: for resonance to occur, the frequency of the tuning fork has to become equal to some resonant frequency of the organ pipe. Okay, so the frequency so F has to be equal to some 2n plus 1 times 1 by 4 L effective into root gamma RT by. So this is the sort of general formula that you have to understand. This is the condition of resonance. Okay. So what do we mean by L effective? Let's understand in the diagram. So L effective here means that if I filled up water up to this height, then the resonating column's height now becomes this one. This is our L effective. So L effective in general should be equal to the original length minus H. Okay. Typically plus end correction also. So that end correction here is negligible in this particular question. But in general, you should know that the end correction value is 0.6 times the radius of the pipe. So in case you get a question where end correction is also given, you should know that actually the pressure node that occurs slightly above this, occurs slightly above the open end, and the antinode occurs exactly like this. So if it is 2n plus 1n, so for example, if it was fundamental, then there is only one node and antinode. If it is first overtone, then there are two antinodes and two nodes. Like that, if it is 2n plus 1n, okay, there is n antinodes and n nodes, like that. So anyway, so this becomes the formula. So let's say we have some kind of situation like this. Now the next consecutive, so if resonance, if first resonance is for H equal to some height H1, that means F is equal to 2n plus 1 upon 4 times L minus H1 speed of sound. If the second resonance is for H equal to H2, where H2 is equal to H1 plus some delta H, then that same frequency is equal to some new resonant mode. So basically, coming back to this diagram, you'll understand. If there's a new resonant mode for a slightly greater height, so So if my original resonant mode for h equal to h1 was occurring for this side here, that was because for that particular thing, this at this height we had an anti-node. Then somewhere above we had a node, then again an anti-node, then again a node, and like this we'll be at a node. Okay. Now from here, if we start increasing the water level, the next time we will get a resonant mode is when the water level reaches here. So this should be our delta H, and this level should become our H2. Whereas this was at H1. So the next resonance will occur when the same frequency is giving us which mode of this thing. So you can see that because the height is reduced, so this will become 2n minus 1 upon this is for the second resonance. Or in other words, H2 which is equal to H1 minus delta H. Okay. Here delta H has to be equal to how much? It has to be the distance between antinode and antinode. So it has to be equal to lambda by 2. This is the most important thing to understand. If you're gradually increasing the level of water, you will not get resonance till the pattern over here matches the frequency of the tuning fork which you have used above. Okay. So for that to occur, the frequency of the tuning fork is a fixed value. So the wavelength of sound it is creating is a fixed value. So that wavelength is such that there is a fixed distance between antinode and antinode. So only when your water level reaches a new antinode's position, the whole column of air inside will start vibrating in resonance again. So that's why your delta H has to be equal to lambda by 2. So going to our earlier question, that is the key to understand now, that the height is increased from 5 to 23. So from that you know that in our question H1 was 5 centimeters, H2 was 23 centimeters. So we know this now. Delta H from first to second resonance is equal to 18 centimeters. So that is equal to lambda by 2. So use that, and along with that use the speed of sound. But just to make the calculation easier here, let us change the speed of sound's value so that and do the calculation more comfortably. Let's take it as if it is more because maybe the temperature of air is more than standard atmospheric temperature. So take speed of sound. So from this now get the frequency and get the length of the pipe. Also given that there was a total of 9 resonances. Okay, so try this out. So nobody still got the answer. Janmay, Manishka, anybody got the answer? Yeah. Manishka, you got some answer, let me check. Frequency is coming 10 hertz. No, centimeters mein na beta. So you have to convert to meters. See, your lambda for the tuning fork sound created is coming 36 centimeters. That is 36 into 10 raised power minus 2 meters. And your speed of sound I've asked you to take as 360 meters per second. So frequency becomes 360 divided by lambda. On 1000 hertz. 1 kilohertz. That is the frequency. That's the first thing. Okay. You just have to use this. Now, what about the length? So you'll also understand in terms of the length, what is happening is this is the position of the first resonance. Then second, then third, like this. This is, let's say, the ninth resonance. So this was this. So between first and second, it is lambda by 2. Between second and third, it is lambda by 2. So like that, between 8th and 9th, it is lambda by 2. And when we add the final resonance, then this distance here is lambda by 4, because each of the resonances corresponds to an antinode. And finally at the top we have a node. So the length becomes how much? It becomes lambda by 4, that is at the top. Okay, plus, you know, how many of these will occur? There will be 8 times lambda by 2, because the distance between the first resonance height and the ninth resonance height, every time you are going from one resonance to the next one, your height is increasing by lambda by 2. So from 1 to 9, you are increasing the height 8 times. Okay, so it's 8 times lambda by 2 plus the height of the first one. So this becomes it. Okay, so this is 9 centimeters plus 8 times lambda by 2, and lambda by 2 was 18 centimeters plus 5 centimeters. So 9 plus 64, 128. This is the length of the organ pipe. Okay, so hope this is clear to all of you. This is a very standard type of question. I mean, this is a mains level question. Okay. Next up, let's look at another type of question for standing waves. So in this example, what is happening is, if we have an open organ pipe of length L. Now this is such that the fundamental frequency for it is, let us say, 240 hertz. Now a hole is made at x equal to L by 5 from its closed end. So find the new fundamental frequency. Again, neglect end correction. So what is happening is, when we next do this, the same organ pipe now, now what we do is we make a hole somewhere here. A distance of L by 5 from the closed end. So what is the new value of fundamental frequency that is there? Just try this out. So anyone got the answer yet? So people, so what's going to happen here when we introduce the hole over there, wherever the point where the hole is there, the air inside is in contact with the atmospheric air outside, directly in contact. So if the air is in direct contact with the atmospheric air outside over there, that has to become a pressure node. So अभी क्या हो रहा है, second situation में where there is a hole present, forcefully that position of the hole is also a node, and obviously the open end is also a node, and the closed end is an antinode. So whatever fundamental frequency and overtones are present, they have to be with that constraint, that not only the open end is the node and the other end is the antinode, but in between that point where the hole is there, that also has to be a node. So your whole standing wave pattern has to be with those three constraints. Instead of two constraints, just the two endpoints being node and antinode. Now there's a third constraint, that the position of the hole also has to be a node, has to be a pressure node. So solve the problem with that thing in mind and you'll get the answer. Okay, so I have got one answer. Let me check. (300 Hz), Malishka, let me check the answer, please. So what is happening in the case of the organ pipe with the hole is that in any resonance condition or in any particular overtone, this has to be a node, this has to be a node, whereas this has to be an anti-node. So this length, which is L by 5, and this length, which is 4L by 5. So this 4L by 5 space has to be the distance between nodes. So it has to be some multiple, let's say n of lambda by 2. Whereas at the same time, this length L by 5 has to be an odd multiple. So it is, let's say, some 2m plus 1 times lambda by 4 for the antinode end. So our lambda has to satisfy both the conditions. Okay. So the maximum value of lambda satisfying both conditions corresponds to the fundamental frequency. The new fundamental frequency. Okay. So let's see how we can work that out. So let's write this. 4L by 5 is equal to n lambda by 2 as our equation 1. And L by 5 is equal to 2m plus 1 lambda by 4 as our second equation. And now let us just divide these two equations. So dividing this side, we'll have 4 is equal to n by 2 into 2m plus, or this 2 will come in the numerator first. Or n upon 2m plus 1 has to be equal to 2. So we have to find two numbers, a general number and an odd number whose ratio is 2:1. Okay. So this becomes like a series. Okay, it's a series of n and 2m plus 1, such that the first member of this series is basically 2 and 1. The second member of this series has to become 6, 3, because this always has to be an odd number, and n has to be double of that. You can see here that n has to be 2 times 2m plus 1. And the next one will become next. So this corresponds to the fundamental mode. This corresponds to the first overtone, and so on and so on. So in the fundamental mode, okay, my L by 5 has to be equal to 2m plus 1 lambda by 4. So that will become 2m plus 1 is 1 into lambda by 4. Or we can say that 4l by 5 is equal to n times lambda by 2. So n is 2. So whichever way we say it, we get lambda naught as 4l by 5. In the first overtone mode, L by 5 will become 3 times lambda naught by 4. Or if we go with the second equation, 4L by 5 will become 6 times lambda naught by 2. So whichever of the two equations we use, our lambda naught will become 4 by 15. And so on and so forth. This is a series. So the fundamental mode has a frequency of 1 by lambda naught into speed of sound. So that in this case is becoming this much. 5 by 4L into speed of sound. This is with hold. And the original fundamental frequency is just 1 by 4L into speed of sound. That is original closed organ part. That one. Okay. So from this 1 by 4L into whatever speed of sound on the day is equal to 240 hertz. So the new fundamental frequency become 5 times 1 by 4L speed of sound. So it is 5 times 240. So it's 1200 hertz. This should become our answer. Okay, so I'm just minimizing this to understand this thing. It must have a pressure node at that place. Okay, so that's the fundamental concept we are using over here. So hope this is clear. Okay. Now let's. So these were some revision questions for your standing waves in sound. Now let's come back to some more general type of questions in sound. So next up, I'll pick up a question or two from Dopplers Effect. Okay, so suppose we have this kind of situation where a point source of sound is moving in a circular path like this, and an observer or a detector is somewhere over here. So point source of sound moves in uniform circular motion at speed, let us say 6 meters per second, and radius let us say radius is 12 meters. Now the source emits sound at frequency of say 500 hertz, okay, and speed of sound is that's approximately 330 meters per second. Now a detector is stationary at a position D at 24 meters from the center. So what we have to do here is find the minimum and maximum frequency of sound detected. And the time intervals for frequency heard to change from minimum to maximum frequency maximum to minimum and maximum to original frequency of the source. Okay, so again a very standard type of question of Doppler's effect. Just work this out. So understand the geometry of the question first, then I'll give you the individual parts again. So just try this question out, people. Okay, so people, anybody got the answer in this? Not yet. It's very surprising because this is a very standard type of question. Anyway, so I'll explain to you. So what happens in a situation like this is maximum frequency is heard when the approach velocity is maximum, and minimum frequency is heard when the separation velocity is maximum. So this is more about mechanics than sound actually. Understanding the relationship between approach and separation velocity. So if you have a detector somewhere over here, yeah, so we have a detector somewhere here, and the source is moving around like this. Okay. Then at any point of time, the approach velocity of the source will become maximum when the source is at a position like this. That when you draw the tangent, it's passing through that point. This kind of situation. So when the source is over here precisely, with the source's velocity along this direction, this is when the frequency heard is maximum. So at that point of time, the source's position is like this. Whereas when the source, on the other hand, is at some position symmetrical on the other side like this, this is when the frequency heard will become minimum because the source is sound. So this is when the separation velocity is maximum. So that means frequency is minimum. The Doppler shifted frequency for the detector, that's when that's minimum. Whereas in this position here, the approach velocity is maximum. So the Doppler shifted frequency is maximum. So anyway, first part we just had to find out that maximum and minimum frequency itself. So that was actually a very easy part. All you have to do is you have to substitute in the formula of Doppler shift. So for approach, Doppler shifted frequency is V upon V minus Vs into F. So for maximum value, the value of Vs over here should become equal to the actual speed of the circular motion. So that was how much? The speed of the circular motion was 6 meters per second. So correspondingly, your F maximum will become 330 upon 330 minus 6 into 500 hertz. Now here we can do a bit of binomial approximation to make the calculation easier. We can write this as 1 minus 6 upon 330 to the power minus 1 into 500 hertz, taking 330 common in the numerator denominator. So then we can approximate this as 1 plus 6 upon 330 into 500, or 1 plus 1 by 55 into 500. So that is 500 plus 500 upon 55. So it is nearly this is the maximum frequency. Now, very similarly, I want you to calculate the minimum frequency yourself. It's very easy. You have to just adjust the formula. Okay. And the minimum frequency will occur when the position is over here. So I'll just minimize this for you to see the calculation carefully. It's quite easy actually. Eighty. Yeah, correct. Manishka, the minimum frequency is correct. So now come to the last part of the question. The time interval for the frequency to change from minimum to maximum, maximum to minimum, and also maximum to original frequency. So as this is going round and round like this, how much time it takes for the frequency to change from maximum to minimum, then again minimum to maximum, then again maximum to minimum, like this. Okay. So just for the benefit of others, I'm showing you how to calculate the minimum frequency. So when the source has separation velocity of Vs, then the Doppler shifted frequency f prime becomes V upon V plus Vs times f. So here the separation velocity's maximum value is equal to 6 meters per second at the other position which I had shown you above. So that is when the frequency heard is minimum, when this is maximum. So F minimum just becomes 330 upon 330 plus 6 instead of minus 6. So again, when you do the binomial approximation, I mean, this becomes 1 plus 6 upon 330 to the power minus 1 into F. So with the binomial approximation, this becomes 1 minus 1 upon 55 times 500 hertz. So it becomes nearly 490.9 or something like this. This is the minimum frequency. So this is the first part done. Okay. Now you have to calculate the time taken for the frequency to change from maximum to minimum and vice versa. So whatever time you are here, just a moment. So let's say you are here at time t1. Then to go from here to here, time t2. Okay. And then you come back here at time t3 again, which is t1 plus 1 whole cycle, like that. So how much time that takes? So for that we have to know the angular displacement so that we can calculate it in terms of time period. So for the angular displacement, you have to understand that this radius was 12 meters. Okay. And this distance from the center to O, let's say this D, this was 24 meters. Okay. So that means if this angle is a theta, so that theta is how much? Theta is sine inverse 1 by 2, or it is pi by 6. Okay. So you can see to go from this position, the maximum frequency position to minimum, the angular displacement is actually this much from here to here. So it is how much? This is 30 and this 30, 60. So it's 300 degrees. Whereas to go from here to here, it is just 60 degrees. 30 plus 30, 60. So like that. Okay. So you can see that for the second part, for maximum to minimum, the angular displacement is actually in my figure what was 2 pi minus 2 theta. Oh, sorry, theta is cos inverse, not sine inverse. So cos inverse half will give you pi by 3. That's what I thought, it was looking a little odd. So this will become pi by 3. So that one will be 240 and this one will be 120. 2 theta will be, okay, so this one will become 2 pi minus 2 pi by 3 or 4 pi by 3. So therefore the time interval will be delta theta upon 2 pi times the time period of the circular motion. Capital T is the time period of the uniform circular motion, which also I'm coming to, but so this will become, this is it. This is 2/3 of the time period, and the time period is 2 pi r divided by speed. Okay. So it will become 4 by 3 pi into 12 meters divided by 6 meters per second. So 8 pi by 3 seconds. This is the delta T to go from maximum to minimum. And in the figure, you can see that minimum to maximum is just half of this. So delta theta for that is 2 theta. So that is 2 pi by. So the time is 1/3 of one time. Because this was 2/3 of one time period, this is 1/3 time period. So this is this part, and also you have to calculate the time taken to go from maximum to normal frequency, maximum to the original frequency. So first I'll just take you to the diagram so that you understand that again. So understood. In this circular motion, as you're going from this maximum frequency position to the minimum frequency position, you're making an angular displacement actually of 240 degrees or 4 pi by 3. And as you're going from minimum to maximum, oh sorry, it's the other way. Maximum to minimum is this, and minimum to maximum is the other one. Okay. So here, this is actually minimum to maximum. So the top position was minimum, and the position below, which I had marked in red, this is minimum to maximum. And this was from the blue position where it was minimum to the red position below where it was maximum. So this is maximum. So that 4 pi by 3 seconds or 1/3 of the time period is in going from this position here, this position where it is minimum frequency to where it is maximum frequency to this. This is 1/3 of the time period. Because again, back from maximum, back from minimum to maximum, this one, that is 2/3 of the time period. Then again 1/3 of the time period. Then again 2/3. Okay. Now the last part, where at which position the frequency will be normal. That is when there is no approach or separation velocity. So that is this position here and this position here. You can see that these two positions, if I mark this as one position, so here you can see that the velocity of the source has no component towards d. And again, at this position, the velocity of the source has no component towards d. So these are the two positions, let's say P1 and P2 are the two positions where there is no Doppler shift. Let's say the maximum position I'm labeling as P3. So P3 to P1, that takes 1/6 of the time period because the angle is 60 from here to here. Okay. Then from P1 to, let's say, P4, where it is maximum, okay, the frequency is minimum, separation velocity is maximum. That again takes t by 6. Then to go from P4 to P2, that is from minimum frequency position to normal frequency position, the angle you can see is 120. So 120 is 1/3 of a cycle. And again, to go from P2, where the frequency is normal, to P3, where the frequency is maximum, again takes 1/3 of the cycle. So, this kind of question also you can get, which is a hybrid of mechanics concepts and Doppler effect. So that's that. Okay. So if there are any particular questions from your booklet or some test paper or something which you required help from me, particularly for sound and all, please send it to me on WhatsApp. You can just personally send a message to me. I will send you the solution or help you out with some hints, etc. Okay. Now let's move on to another type of important question to do with standing waves. And for this, now I'm coming back to standing waves in a string. Okay, so let's look at that. So we now have this situation. We have a lighter string, and in comparison, we have a heavy gauge string. Just to make this more discernible, we change the shade of this also. So I have this situation. So this is 2 lambda, and this is lambda. So linear mass density are in ratio 1:2. Okay, and this is of length L2 equal to, let us say, 180 centimeters, and this length L1, which is, let us say, 200 centimeters. Okay, and this point. So what we are also doing here is that so this junction is at a narrow aperture in a wall. So this is a fixed wall with a small aperture. Okay. And of course, these are also fixed walls. So we have this kind of arrangement over here, and the tension is, so instead of lambda, let's use the variable mu over here. And so the common tension is equal to, let us say, 1200 newtons. And on this side, we have linear mass density, which is, let us say, 2 grams per centimeter. And on this side, we have linear mass density, which is, let us say, 4 grams per centimeter. Okay. So we have to find the fundamental mode of vibration. Frequency. And we have to find the formula for the nth overtone mode's frequency. So these are the two things that we have to do over here. So again, you have to understand, because the junction of the two strings is at that narrow aperture, so the junction is also forced to act like a node. So again, this is somewhat similar to the problem we were discussing earlier today of sound, where you add that additional hole in that organ pipe. So this is again a standing wave pattern with three constraints. The two end points have to be nodes because they are rigidly attached to walls. But now even the junction point is a node. Okay, so anybody got an answer yet? Okay, so let's understand what's happening here. So see, in this question, this will have to be a node. This will have to be a node, and this point here will have to be a node. But also you'll understand that on one side you will have a different wavelength compared to the other side. So in string 1, your wavelength will be equal to square root of t by mu1, common tension but divided by mu1 into 1 upon frequency. And the second one, this will be square root of t by mu2 into 1 upon it. Okay. So that is why you can see that your lambda 1 is to lambda 2 will in fact be square root of mu2 is to square root of mu1, which over here is an irrational number, but doesn't matter. Just take it as 1.4. Or we can just make the question a little easier by just taking an easier value of mu. Suppose this is 1 gram per centimeter. So then this changes to 2:1. This whole thing just becomes a little bit easier, but anyway, the method is the more important thing here. So generally they give numbers where your square root cancels out. So it's like either 1 and 4 or 4 and 9 or 9 and 25 gram per centimeter, whatever language. Okay. So this is your lambda 1 by lambda 2. Okay. Now you can see here that this has to be node to node. So this has to be an integer multiple of lambda 1 by 2. and this same length on this side has to be some other integer multiple of lambda 2 by 2. So that is the concept that you have to understand, and this is 200 centimeters, that is 180 centimeters. So that is like a constraint that we have now. Okay. So we have lambda 1 is to lambda 2 was 2 is to 1, and L1, which is 200 centimeters, that has to be some integer multiple of lambda 1 by 2, and L2, which was 180 centimeters, that has to be some integer multiple of lambda 2 by 2. So equation 1, equation 2, and equation of 3. Okay. Now here the minimum possible values of n and m as whole numbers or integers will tell us a fundamental frequencies formula. Okay, so that is a concept. So if you just do equation 2 divided by equation 3, you get on this side 200 by 180. That should be equal to n by m, lambda 1 by lambda 2. So 10 by 9 is equal to n by m into lambda 1 by lambda 2 is 2. So n by m is 5 by 9, or you can say n is to m is equal to 5 is to 9. So in other words, standing waves corresponding to lambda 1 and lambda 2 such that L1 is equal to n times lambda 1 by 2 and L2 is equal to m times lambda 2 by 2, and n is to m is equal to 5 is to n. Are created. The standing waves have to support this condition, okay, that this length has to be some integer times lambda 1 by 2. This length has to be some integer times lambda 2 by 2, where the ratio of these integers is 5 is to 9. Okay. So first of all, let us see what are the values of n and m possible. So n and m as a pair, the minimum possible value is 5 and 9. Because if n is smaller than that, okay, then m will not be a, this is the smallest ratio of two integers which have a ratio of 5 is to 9. If that ratio, for example, had come out to be 4 is to 6, then it would have broken down to 2 is to 3. But here 5 and 9 are co-prime. Okay. The next possible pair is 10, 18. The next possible pair is 15, 27, and so on and so forth. Okay. So minimum value of n is 5, and similarly of m is 9. So fundamental mode f0, it corresponds to frequency being minimum and lambda being maximum. So lambda being maximum corresponds to n being minimum, because if you see now, this fundamental frequency will be, how we'll calculate it, it is 1 by lambda 1 square root t by mu 1, and that should be equal to 1 by lambda 2 square root t by mu 2. Okay. For lambda 1 and lambda 2 to be their maximum values. So remember, we had n times lambda 1 by 2 is equal to L1. So lambda 1 is equal to 2L1 by n. So lambda 1's maximum value is 2L1 by 5. Similarly, we had m times lambda 2 by 2 was equal to L2. So correspondingly, lambda 2's maximum value is 2L2 by 9. So when you substitute here, these are their maximum values. So they are this and this. So this is becoming 2/5 of 200 centimeters or 4 by 5 meters. Okay. And this is 2/9 of 180 centimeters. So that is 2 by 9 into 180 or 40 centimeters or 0.4 meters. Yes. Okay. So that fundamental frequency is either 1 by lambda 1, which was lambda 1's maximum value, which was 0.8 meters, into square root of tension divided by mu1, which was 1 gram per cc, so that is 10 kg per meter, or that is the same thing as 1 by L2, where 1 by lambda 2, where lambda 2's maximum value is 0.4 times square root of 120 divided by this will become 40. Okay. So that's why you can see this and this are ultimately the same. And the value of that fundamental frequency is this much. It is 5 by 4 into 2 times square root 30 hertz. So it is this is the fundamental. Or if I had selected a better value of tension, like maybe 1000 newtons or something, you would have got a clean value. But this is the fundamental frequency, okay? And this fundamental frequency corresponds for n equal to 5 and m equal to 9. So that corresponds for lambda 1 equal to 0.8 meters and lambda 2 equal to 0.4 meters. Okay. Now the first overtone will correspond for n equal to 10 and m equal to 18. So when n is doubled, what will happen to lambda? Lambda 1 will become half. It will become half. So the frequency of the first overtone will be the second harmonic of fundamental. And like that, the frequency of the nth overtone will become the n plus 1th harmonic of the fundamental. So this is the concept that you have to understand here. First of all, this thing that frequency is common. Okay. Tension is common, but mu is different on both the sides. Therefore, lambda is different. So to apply two standing wave constraints, okay, that L1 is an integer multiple of yeah, Manisha, I'll just come to your question. Yeah, I'll come to your question. Okay, so hope this question is clear. Okay, people. Unfortunately, I've suddenly had a video. I've suddenly had an internet outage here, so my PC is out of internet connectivity, and I'm right now like on 4G, so I'm connected via phone to you. So let me see. It will take some time before I can sort out the internet issue. So we will conclude the class today. I will just send you the. I will send you the whiteboard notes. Now, Manishka, to answer your question about Narsi Monji, right? That's what you asked. Specific topics for NMIMS, which is Narsi Monji. Yes. I haven't seen too many papers of this, but last 2-3 years, some of my students have been taking the entrance exam. So what I have observed, Manisha, is that they generally, definitely ask a lot of questions from the electromagnetism part, the class 12 heavy portion of the topic, which is from electrostatics right up to electromagnetic induction and AC circuits. Especially a lot of things on things like, simple magnetism, uniform circular motion of charged particle, helical path. Then they won't ask something very complicated like charged particle in electromagnetic field. They'll just ask simple magnetic field mein helical path, magnetic field mein circular path, then simple motion generated EMF type of questions, induction type of questions, mutual inductance, self-inductance, LR circuits, then RC circuits, transient analysis. Then again, in current electricity, they don't ask too much about complicated things like symmetry in circuits and all that, but direct things like Wheatstone bridge application, potentiometer application, those kind of things. So class 12 syllabus is generally in 12th also that electromagnetism part is given a lot of weightage in NMIS, whereas in mechanics and all they tend to ask less number of questions also and more fundamental questions, not your JEE standard type of questions. So that is what I have observed so far. But again, I think if you can get hold of some mock papers or some previous year papers, you will also get some idea about the trend yourself. So I'm trying to see if my internet connection can be refreshed, but as of now, it's just showing that the server is down. So we will conclude today's session, which anyway almost time, and I will send you the whiteboard notes and the recording also. Okay, so that's it for today, guys. If you have any further doubts in waves, etc., please send it to me. And next time we will discuss some other topics. So I'm thinking, transistors and semiconductors. Okay, so we'll discuss that also. What about wave optics? Do people need? So I'm just going to unmute you all. So in generally speak. Yeah. What about wave optics? Fine with that? Or
Sir, actually, I was particularly asking for transistors as in 12th that had been cut off from a portion, so we have not studied that at all. And so I observed questions from transistors, maybe 1 or 2 in JE and NMIMS also. So I wanted a little help in that.
This is important. As you know, it is not part of JEE advanced syllabus. Okay, but in JEE mains, semiconductors, logic gates, transistors, diodes, okay, those kind of circuits, PN junction diodes, semiconductor diodes, etc., as well as semiconductor transistors. That's important. Okay, so we'll have a discussion about that. But that's all, very theory type of thing. It's like the applications aren't very difficult. So I will also send you some reading material if you can, go through that. And do you have any study material for transistors and semiconductors? Are you people following any standard kind of study material for?
Sir, we have NCRT for class 12 and SL Aurora.
NCRT is too lengthy, beta. For semiconductors, you'll have to read too many things. I mean, concentrating on JEE, you don't need that much. For boards, it's okay for theory questions. Okay. You have HC Verma part 2 also, right? All of you.
Yes.
So the part which is given for semiconductors in HC Verma part 2, that is more than enough. Both that as well as logic gates, both the chapters in there, that is more than enough. So I will teach you the part, the conceptual part, and we will refer to HC Verma for your self-study from that. So it's really all about theory. So before next lecture, if you people can just read the initial part of semiconductor theory, the concept of the band gap and energy level diagrams, and those kind of things, so that we can concentrate more on the applications. So we'll straight away start with PN junctions and their applications, and then from there into transistors. Okay. So just make sure you read the concepts of the electronic band theory for semiconductors, okay, and the concept of dopant and N and P type semiconductors. If you just read that part from HCV and come prepared in the next, I'll help you out with that. Okay, people.
Yes, sir.
Right. So that's it for today, people. Then just remember to read through semiconductors, the initial part up to doping of semiconductor to get impure semiconductor or P and N type semiconductor. From there on, from the junction concept onwards, I will teach you in the class. Okay. Okay, that's it for today's lecture then.
Thank you.